I'm going to start this lecture by defining a rather strange function called an area function. This is defined to be the integral from 0 to x of t dt. For example, g of 1 is the area of this triangle. If we let the horizontal axis be the t-axis, then the curve y equals t is this diagonal line, and so the integral from 0 to 1 is the area of this triangle, and we can compute that area using 1/2 base times height to get 1/2. Or g of 2, this would be the area from 0 to 2 under the same curve, and again by 1/2 base times height we see that g of 2 is equal to 2. So why am I introducing this function? Well, let's try to compute more generally what is g of x. Well, that would be the area under this curve from 0 to x, and again by 1/2 base times height, that would be 1/2 x squared, and we can observe that that is an antiderivative of this curve, f of x equals x. And this is a phenomenon which occurs more generally. The fundamental theorem of calculus, at least the first part of it, says the following. If we fix any real number a, in the previous example a was equal to 0, then for any function f of t, if we integrate from a to x, and then take the derivative with respect to x, then we get back at the original function. What this means is that this integral, this area function from a to x, is an antiderivative of f of x. Now, of course, this is not the general antiderivative because it's not a family of functions, it's just a single function, so it is a particular antiderivative of f of x. For example, if we're trying to compute this expression, what is this? This is the derivative from 3 to x of this function here in t. Well, the fundamental theorem, part 1, tells us to simply replace t everywhere we see it in this function with x. Okay, what this means is that this integral from 3 to x, ignoring the derivative, the integral itself is an antiderivative of this function because its derivative is equal to this function. Okay, let's do another one of these. The only thing different here, well, we have a slightly different function inside, but you'll notice that instead of having just x as this upper limit, we have x squared. And so we can't really use the fundamental theorem directly. Let's let g of x equal this area function that we would know how to compute the derivative of, namely from 5 to x rather than to x squared. Then what we're being asked for is the computation of the derivative of g of x squared. That would be this integral here. Well, we know by the fundamental theorem that g prime is equal to x over x squared plus 1, just replacing t with x in both spots here. Okay, well then we can apply the chain rule. The derivative of g of x squared is equal to g prime of x squared times the derivative of x squared. That's the chain rule. And now we can focus on these separately. We already know what g prime is. It's this fraction here, x over x squared plus 1. And so plugging in x squared to that, we get x squared over x squared squared plus 1. And the derivative of x squared is equal to 2x, and now we can simplify to get this. Now the second part of the fundamental theorem of calculus is more important than the first, in my opinion. This is the method for computing definite integrals using indefinite integrals. If f of x, capital F of x, is an antiderivative of little f of x, then the definite integral of little f of x from a to b is equal to this expression here. And this funny business here, this capital F of x with a big line a to b, this is the notation that we use to indicate this difference. We evaluate the antiderivative f of x at b, and then again at a, and we take their difference. That's what this expression here means. Now, will it matter which antiderivative we use? Remember that a function has many antiderivatives if it has one at all. So what happens if we use a different antiderivative? The answer is, well, you'll get the same answer. You see, if I use f of x plus c rather than f, then this difference here, f of x plus c evaluated at b is f of b plus c, and this antiderivative evaluated at a is f of a plus c, then this difference, you'll see the c's cancel. And so that difference is the same as the original difference. So it really doesn't matter which antiderivative we use, it's just that if we find some antiderivative of little f, then we can just compute a difference rather than a full integral. Okay, let's see an example of this. let's compute the area of this shaded region under the curve y equals cosine x. Well, the idea is this. We know that sine x is an antiderivative of cosine x, and so the fundamental theorem of calculus tells us how to compute this definite integral. Yes, the limits were from 0 to this point of intersection, right? And that's x equals pi over 2. That's why I'm doing the integral from 0 to pi over 2 of this cosine function. Okay, well, the fundamental theorem tells me to use the antiderivative, sine x, and evaluate that from 0 to pi over 2. In other words, I just plug in pi over 2 into sine, and then I plug in 0 into sine, and I take the difference. Okay, well, sine of pi over 2 is 1, and sine of 0 is 0, and that difference is 1, which tells me that the area of this region is exactly 1. Now, I really want to emphasize how special this was. If we didn't know the fundamental theorem, then we would have had to compute this area by setting up this limit of Riemann sums, which I have to admit is extremely difficult to compute directly. So really, this fundamental theorem is a vast improvement on this method. Let's use it again to compute the integral from negative 1 to 1 of the function 1 over 1 plus x squared dx. Well, we know the general antiderivative of 1 over 1 plus x squared is arctan x plus c. This is one of the basic integrals that you've memorized. Then, the fundamental theorem tells us that this integral is found by evaluating arctan x from negative 1 to 1. And we're ignoring the plus c here when we're dealing with these definite integrals. We've already decided that the c's would cancel in this process, so we ignore the plus c for definite integrals. Okay, well now let's plug in 1 into arctangent x and negative 1 into arctangent and take their difference. Okay, arctangent of 1 is pi over 4, and arctangent of negative 1 is negative pi over 4, so we get pi over 2 as the exact value for this integral. So to recap, the first part of the fundamental theorem of calculus tells us that integration and differentiation are inverse operations of each other. If I start with a function f, integrate it from a to x, and then take the derivative with respect to x, then I arrive back at the original function x. So in that sense, integration and differentiation are inverse operations of each other. The signed area under the graph of f from a to b is equal to the net change in an antiderivative of f of x from a to b. That's what the second part of the fundamental theorem was telling us. And this is an excellent way to evaluate integrals. From now on, we're never really going to compute Riemann sums, so this is a wonderful improvement on our method for computing definite integrals. Now in the next video, we're going to discuss a new technique for integration called substitution, or sometimes U-substitution, and this will allow us to compute a much wider range of integrals. But for now, please try to use the information from this video to answer these questions, and I will see you next time.